Now?
Now we are able to see it.
Yeah, yes. So shall we just have a quick recap of what we are discussing presently? Hello. So,
Yes,
so
ma'am.
far, yeah, what we have discussed so far, just give me a quick recap. So we are discussing about CMOS logic. First, we started with CMOS, started with standard CMOS or full swing CMOS. Full swing CMOS, or it can also be called as static CMOS. So in that, we have a pull down network, we have a pull up network. The pull up network is connected to supply, pull down network is connected to ground. Input is given between the gates of pull down network and pull up networks, and output will be taken at the drains of both pull down network and pull up network. So the advantages of that is it has no static power consumption, no static current. That means when the output is either 1 or 0, exactly it doesn't have any current flowing through it, but the current flows only when the input is changing from 0 to 1 or 1 to 0, only in the transition periods. So it has more noise margin and full swing. So, but it has more number of transistors to implement the logic. So the static CMOS logic requires 2n transistors, right? 2n transistors to implement a n variable function. Then we have another logic, pass transistor logic, in which we can use either NMOS or PMOSFET as a pass gate. If you are using NMOSFET as a pass gate, it is called as NMOS PTL logic. And if you use PMOS as a pass gate, it is called as PMOS PTL logic. So the advantage of pass transistor logic is any logic can be implemented with less number of transistors. But the problem with the pass transistor logic is it has a threshold drop. If you use PMOS logic, we will not get strong 0, but we will get VTP. If it is a NMOS logic, we will not get strong 1, but we will get VTT minus VT. That some of you have observed in the lab also. Okay, and then to avoid the threshold drop in the pass transistor logic, we have developed the transmission gate logic that also we have seen in the earlier classes. A transmission gate is a combination of PMOSFET and NMOSFET, as we have both PMOS and NMOS in parallel. So when PMOS is off, NMOS is conducting, and when NMOS is off, PMOS is conducting. So we do not have the threshold drop in the transmission gate logic. So already we have seen, so this is a transmission gate symbol, and we have seen some circuits also using transmission gate. It's a multiplexer with active low logic, and it's a XOR gate. And already I have asked you to trace this, and it's a 2x1 mux and 4x1 mux and 8x1 mux also. And also have given you another small circuits also, how we can develop them with transmission gate logic. Yes, can I go further with this? Hello.
Yes,
Hello.
ma'am.
Yes, ma'am.
Yeah. So now, in addition to the transmission gate logic, we will see some of the other variations in the pass transistor logic. Just let us again go this. You know pass transistor logic, right? So what's this is already I gave you general configuration of pass transistor logic. We have X and Y here, and B and B bar here. Depending upon the values of X and Y, we can get any logic required using pass transistor logic. Already you know that. And this is typically an AND gate in pass transistor logic. We also know it. Okay. And this also have explained you. So when what is the main problem with the threshold drop is whenever we connect the output of a pass gate to a CMOS inverter, because of the threshold drop, so the CMOS inverter will lie in B, C, D regions of its inverter characteristics. So there is a current flowing in the CMOS inverter. because we are not giving strong one. So that's why CMOS inverter also consumes power. So that's the main problem with the pass transistor logic. Pass transistor logic is sometimes called as NMOS only logic because NMOS PTL has only N MOSFETs. PMOS only logic means PMOS pass transistor logic has only P MOSFETs. That's why we can call them in that way also, NMOS only logic and PMOS only logic. Okay, so the threshold drop is a big problem. So in it, instead of going for another logic like transmission gate, what people are doing is say they are using some level restoring transistor, okay, at the output of the pass gate to cater to the deficit of the threshold drop. Okay, so let us see, this is some alternative solution. See here, this is a NMOS pass transistor, right? You know it, A, B. And what will be X? X will be, and generally V minus Tn, we know that X will be V minus Tn. But here what is the thing here is, see, for example, when you will get threshold drop in this NMOS pass transistor, when do we get threshold drop? When output is high, right? When output is low, we don't have any threshold drop, yes or no? In NMOS, we have threshold drop only when output is 1, correct? Hello.
Yes, ma'am.
So when X is equal to VDD minus VTN, X will be equal to VDD minus VTN. So when X equal to VDD minus VTN, PMOS, this inverter will be giving you 0 because even though it is not strong one, it is a 1 only. So this inverter output will be 0. Okay, but it will not lie in the A region of the transfer characteristics, but it will lie in the B region. So this is the A region. A region means, so this is E region. So it will lie in the middle. So you have a current, but logically this is 0. Output is 0. So if you give a 0 output to this PMOS FET, what will happen to this PMOS FET? It will be on. So when it is on, automatically it acts as a short circuit. So this point X is tied to 1 VDD. See here, point X is tied to VDD. Do you understand? X, because when this is on, X will be tied to VDD. So what will be the voltage at X? Voltage at X will be VDD. So that's why we call this as level restoring transistor, level restoring. So even though we use a pass transistor logic, by using this level restoring transistor, we will compensate for the threshold drop. You may have a doubt, ma'am, here you have used only one transistor for AND gate and we are using one more level restoring transistor, then is it not a overhead? Don't think that always we are using AND gate. It's an example. We may implement a very complicated logic using pass gate. So if you implement that complicated logic using CMOS, you will get more number of transistors. So instead of that, implementing that complicated logic with pass gate and only at the end, only at the output of the pass transistor logic, just we can use a single level restoring transistor. When we are interfacing the pass transistor logic to the CMOS logic, we can use this level restoring transistor. Are you getting my point? Hello. Hello.
Could you repeat once again?
Yes, here we use this level restoring transistor is tying this input node, this output node X to VDD. So actually X will be VDD minus VTN because of the pass transistor logic threshold drop. But as this level restoring transistor is tying it to VDD, now X will be at VDD. So that is the advantage of level restoring transistor. So when do we use this level restoring transistor? Whenever a pass logic is interfaced to a CMOS logic. Got it?
Yes, ma'am.
Yeah, that's what I mean to say. No, what I'm saying is you may think that pass gate has only one FET, then adding one more FET as a level restoring, is it not a overhead? That some of you may have that question. Yes? So don't think that the pass logic is having only one FET always. Assume that there may be a very complicated logic we implemented using pass transistor logic. Very complicated, say A bar BC plus ABCD plus BC bar plus DC bar, some 6 variable function. That 6 variable function, if you implement in CMOS, it takes more number of transistors. But if you implement with pass transistor, it takes less number of transistors. And then at the output of that PTL, when it is interfaced to another CMOS logic, we can use a single level restoring transistor, so that the disadvantage of pass trans logic will be simply eliminated. That's what advantage of a level restoring transistor. Okay. Hello.
Yes, ma'am. Yes, ma'am.
Yeah. So this is one of the solutions. And then we see another variation in the pass transistor logic. Already we have seen pass transistor logic, transmission gate logic. Please do not confuse between different logics. If you practice more, you will not have any confusion. So another variation in the pass transistor logic is a complementary pass transistor logic, or CPL logic. Complementary pass transistor logic. Okay. So what is this complementary pass transistor logic? Is nothing but we have both pass transistor logic and inverse pass transistor logic in the same circuit. So that is simply a pass transistor, so complementary pass transistor logic. You see here, initially see here, we are giving B, okay, we are giving B to 2 FETs and we are giving B bar to 2 FETs as a gate input. See, B to B bar. So see here, then this is AB plus BB bar. What is this? This is AB plus BB bar. So that is also end. But in the real pass transistor logic, we are using AB plus 0B bar. Do you remember? Hello? Hello?
Yes, ma'am.
In the real pass transistor logic for end, we are getting AB plus 0B bar. But in the CPL, the concept of CPL is we have to use all A bar, B bar to the pass transistor network, and also A bar, B bar to the inverse pass transistor network. So we have to use true inputs and complementary inputs to both networks, original PTL network and inverse PTL network. And also the gates also should be, so the gate inputs also should be complementary. So we should use B and B bar as a gate inputs, like that. So that is why we are using, instead of 0 and B bar, we are using B into B bar. So of course, logically both are same. So AB plus B bar will be AB, correct? Okay. Next, what is the second law? Second one, this one, see, the second one is giving A bar B. See here, A bar B plus what is this? Is B bar into B bar. What is B bar into B bar? B bar. So that is equal to A bar B plus B bar. Can you tell me what is that if you simplify? A bar B plus B bar. X plus X bar Y equal to X plus Y according to absorption law, correct? X plus X bar Y equal to X plus Y. So here we have A bar B plus B bar. So what is, if you simplify, what do you get? Hello? What is absorption law of Boolean algebra? X plus X bar Y equal to X plus Y. Okay. You apply this and tell me what is output you are getting here.
A bar plus B bar, ma'am.
B bar plus A bar. What is B bar plus A bar?
NAND.
AB whole bar, NAND. So what is the advantage of CPL logic? It is giving both true output and complementary output. True output and complementary output. Similarly, you see here, this is A B bar plus B into A B bar plus B into B. I'm speaking about second circuit. Second circuit. So this is A B bar plus B into B B. So A B bar plus B equal to A plus B. So this is giving you OR logic. Then this is A bar B bar plus B bar into B. So B bar into B is 0. So A bar B bar. A bar B bar is A plus B whole bar. So it is giving you both OR and NOR gates. And if you see here, this is A B bar plus A bar B. This is XOR A bar B bar plus AB XNOR. So this is a complementary pass trans logic. So whenever you need both true output and complementary output, XOR XNOR combination or NOR combination, AND NAND combination, or any Y and Y bar combinations, if you require, you can use a complementary pass trans logic. Are you getting it? Hello.
Yes, ma'am.
So this is regarding the complementary fast transistor logic. So far how many logics we have learned? CMOS, standard CMOS or static CMOS or full swing CMOS. And one more thing, if I say just CMOS, it refers to what? Without any prefix or without any adjective, if I just say CMOS, it refers to what? Hello?
CMOS.
No, if I say just CMOS, it refers to which CMOS? Static full swing CMOS. Okay, what we are saying, static full swing CMOS, which is having pull up network as PMOS and pull down network as NMOS. Okay, but if you observe it, actually, pass transistor, say, transmission gate also can be considered as CMOS because it has both N MOSFETs and P MOSFETs, correct? Are you getting my point?
Yes, ma'am.
So if you see logically, it can also be considered as CMOS because all these are belonging to CMOS only. But each and every different logic has its own unique name. So it's a transmission gate logic because we are the combination of PMOS, parallel combination of PMOS and NMOS will be considered as a unit here. So we are calling it as a transmission gate. But if I just say CMOS, it is nothing but static full swing CMOS. You know what is static full swing CMOS, correct? Hello.
Yes, ma'am.
So now we have now CMOS, that is which is static full swing. Then we know pass trans logic. In pass trans logic, we have NMOS PTL, PMOS PTL. Similarly, complementary pass trans logic. Please understand, whenever we have complementary pass trans logic using NMOS, definitely we have complementary pass trans logic using PMOS also, correct? Yes.
Yes, ma'am.
So what makes a complementary pass trans logic with PMOS? We have circuits of NMOS here. So how can we build complementary pass transistor with PMOS? Replace all N MOSFETs with P MOSFETs and just use B bar in place of B and B in place of B bar. That's all. Very simple. Are you getting?
Yes, ma'am.
So just if you interchange this P and B bar, you will get, and replace NMOS with PMOS, you will get complementary pass trans logic with P MOSFETs. Am I clear?
Yes, ma'am.
So now you are in a position to implement any given expression using all these logics, yes? Or do you have any doubt?
Ma'am, one doubt, ma'am.
Yeah, yes.
All the B bars will be replaced with B and the vice versa for B, right?
What is that?
In that like NMOS has to be replaced with PMOS, and the
Correct?
B bar position is to be replaced with B. Like that we
Yes.
have to do, right?
Yes,
Okay.
interchange B and B bar.
We have to interchange it. Okay. Okay, ma'am. Now I
Interchange B and
understand.
B. Because for a PMOS logic, very simple. If you see, go to the basics of PMOS logic. For example, if it is NMOS logic, I think it is actually no. It's very simple actually. Very simple to. If you know the basic logic implementation, it will be very much clear. So this NMOS output is AB. Okay, NMOS output is A into B.
Yes, ma'am.
PMOS output is A into B bar. If we give B here, PMOS output will be A into B bar. Why? Because PMOS will be on only when B equal to 0. That is the basis. Are you getting my point?
Yes, ma'am. Ma'am, that is for what? PMOS. Okay. Yeah, that is for PMOS.
So this is A into B bar. This is A into B. This is A into B bar. So obviously, if you want AB, what you have to do? You have to replace B with B bar.
B bar. Yes, ma'am.
So simple. The logic is A into B bar for the PMOS, A into B for the NMOS. Simple. Okay.
Yes.
So can I go further then to the next topic? Or do you have still any doubts? Yeah.
Ma'am, you can continue.
Hello? Hello?
Yes, ma'am, you can continue.
Yeah, I can. Yeah. So far we have seen all combinational logical circuits, right? So we have to think about sequential logical circuits also. I think before going to the sequential logical circuits, just I want to check you. Are you comfortable with the sizing of the logic, CMOS logic? I think I have mentioned about sizing in the lab. I think in theory class I didn't touch. So just I'll give you an expression. Try that to draw in standard CMOS logic and size the transistors properly. Okay. Just I will give you the expression. Just give me a minute. I'll give you the expression. You take this expression. F equal to AB plus C plus D into E whole bar. Okay. Hello. Do you see the screen?
Yes, ma'am.
Yes, yes.
First, develop the circuit and assume that WP by WN equal to 2 means The basically width of NMOS is twice that of PMOS. Okay, width of NMOS is twice that of PMOS basically. Okay, so taking that basic width, you have to size that in the network. Assume the W by WN equal to 2. So size the transistors such that their delay is minimum. Minimum delay means they should have the delay of inverter, right? Yes. Minimum, that is as that of CMOS inverter. Okay, so first of all, you draw the circuit. I think everybody can draw it, I hope. Draw it and post it. Then size it.
Ma'am, I'm not clear about the sizing. What are we supposed to do? I've uploaded a circuit, but I'm confused,
Yeah,
right?
I'll check. AB plus C plus D into E. Yeah, AB is parallel. The T in series to CD series comp. Yeah, your circuit is correct. Okay, so just I'm giving. What about others? Have you drawn the circuit? Yeah, okay. So you're not confident about sizing. Nobody is confident about sizing. Do you remember we have done it in the lab?
Yes, ma'am.
What is
Ma'am,
the expression? Tell me.
that means you have to just write that 180 nanometer and 200 nanometer.
No. I'll tell you. So what is the expression? Tell me. AB plus
AB plus C plus D into E whole bar.
so AB should be parallel. Then that should be in series with CD series combination in parallel with E.
Ma'am, I have done sizing. Ma'am, can you tell me whether it is right or not?
Hello, all of you please concentrate. What I said WP by WN equal to 2. WP by WN equal to 2. What does it mean? What does it mean? If the basic size of NMOS is W, basic size, if you assume that basic size of NMOS as W, basic width I can say simply, okay? Basic width of NMOS. Later you can understand it very clearly when I am saying about when we go to the RC delay signal. Presently, basic width of NMOS equal to W means, that means 200 nano. For example, if you compare to the lab, what's the basic width? 200 nano, correct? Basic width of NMOS for a symmetric inverter is 200 nano, right? Then, if basic width of NMOS equal to W, what will be the basic width of PMOS if you want a symmetric inverter? That is 2W. That's what it means. But for us, it is different. For us, it is around 5 into 200, something like that you got, right? Hello. Hello.
Yes, ma'am.
80 meter in the 180 P by WN equal to around 4.5 to 5, yes? Around 5 you got. For you in the lab for 180 nanometer technology, WP by WN equal to 5. That's why if the basic width of NMOS equal to 200 nano for you, basic width of PMOS for to make a symmetric inverter is 1000 nano. But here what they give, WP by WN equal to 2. That means if W is the width of NMOS, then 2W is the width of PMOS to make a symmetric inverter. Got it? Hello. That means if I draw an inverter here, you can, if I draw an inverter here, this is W and this is 2W. What does it, that is the meaning of that W to W equal to 2. You are getting my point? Hello.
Yes, ma'am.
So this is R and this is also R. This W is giving it R and this is also giving me R. So what is my aim? I want to make this resistance of all these paths to be R only. Are you getting it? So now check it. You check. So there are two parallel paths. So either this current may flow either through this path or through this path. So first go to this path. In this path, how many NMOS are there? How many NMOS are there? 2 NMOSFETs in series, correct?
Yes.
So 2 NMOSFETs in series means it makes a resistance of 2R, right?
Yes.
If I give W and W, it gives me 2R. But I want only R. The total resistance should be R. If I want total resistance should be R, each MOSFET should have a resistance of R by 2. So I have to give the width of each MOSFET as 2W. Got it? Hello.
Yes, ma'am.
Similarly, you come here. Here again, this is one path and this is other path, right? And in each path, how many MOSFETs are there?
2.
2.
For
So, right?
two,
So, I want a total resistance of R. But if there are 2 MOSFETs in series, they will give you a total resistance of 2R. So, to make only resistance R, I am giving 2W, 2W, 2W. So, this is 2W, 2W, this is 2W, 2W. That's what I'm getting. Is it clear?
Yes, ma'am.
Now, coming to PMOS. Check here. In the PMOS FET, see how many different paths are there? So check it. So here, see, here I can have 2 or I can have 3, right? In a path, I can have either 2 or 3. Are you getting my point?
yes, ma'am.
Yes.
So if this is the path, I can get 2. Or it may be, so the path may be this one. Here also I can get 2. But if it is flowing like this, for example, if this is off and these 2 are on, it is having 3 in the path, correct? Or this may be a path. Then also it is having 3. So what should I consider here? Shall I consider there are 3 in series or 2 in series? If I consider 2 in series, whenever I'm getting 3 in series, then I will get more resistance. But if I size it, keeping in consideration that there are 3 in series, if there are 2 in series, I will get less than R. That's not a problem for me, correct? Hello.
Yes.
Are you getting my point?
Yes.
So at a time, I'm getting 3 MOSFETs in series. Okay. So what should be the sizing? It should be 3 times of the basic width. So what should be the size? 6W,
6W.
6W, 6W, 6W. So it depends upon the circuit actually. Whenever the circuit changes, you have to check all the alternatives. Okay. Whenever the circuit changes, sometimes no, in one path we have only 2 FETs. In the second path we may have 3 FETs. If it is, see here, for example, this is completely parallel, no? But this is a series circuit. So series circuit means there is a possibility of 2 FETs when these 2 are on. When and 3 FETs when these 2 are on. So what are these? I have forgot these literals. You tell me. What are they? This is CD, right? C, D in series, E in parallel. So this is 6W, 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 6W. So is it clear? Any doubt? Hello. Hello.
No, ma'am, no doubts.
Yeah. So now you understand the sizing, right? Do you want to do one more example or you understand it?
Ma'am, one more example will be helpful.
Yeah, okay. Can you just give me an expression? We'll try. Just give me an expression.
Ma'am, A bar B plus A B bar plus
No, no,
A
no.
bar.
Whether, so it doesn't matter whether we have a bar or not, because what makes the difference between A and A bar in the expression? Just we use another inverter, right? Does
Oh
it
yeah,
make
ma'am.
does it make any change in the sizing?
No, ma'am, no change.
But anyhow, okay, okay. I'll take whatever you give. A bar B plus.
B bar A.
Okay. A bar B plus B bar A. So it is not in complementary form. So immediately I'll write that in complementary form. That's the first thing I'll do. Okay. A bar B plus B bar A whole bar. Okay. So, but as this, for this expression, I know what is a complement of this. But in it's not same for all the other circuits, but here particularly what you gave, A bar B plus B bar A you gave me. So A bar B plus B bar A whole bar is nothing but AB plus A bar B bar. I know it because it's an XR function. So this is AB plus A bar B bar whole bar, right? Okay.
Yes, ma'am.
So I'll try to implement this. Already I gave you how to implement this. I gave you one way. The second way I'm using just by using a dual network, I'm doing it. So I gave you already the XOR circuit. Do you remember?
Yes, ma'am.
You might have taken another expression, but anyhow, okay, it's okay. You have taken a very simple expression. It doesn't have any. So AB. Just a minute, it's misbehaving. A bar B bar. And here I can have, I'm using the dual network here. So AB, A bar, B bar. But of course, what I have to do here, I have to add two inverters. So here W, 2W, W, 2W for the inverters. So here in the path I have two N MOSFETs. So I will give 2W, 2W. Here also have two N MOSFETs. I'll give 2W, 2W. Here what is the possibility? In all the paths only two transistors, either this or this or this or this. All the ways only two transistors, correct? Hello.
Yes, ma'am.
4W, 4W, that's all.
4W is for PMOS, ma'am.
Hello.
The 4W, ma'am. Yes, ma'am. The 4W, ma'am. I didn't understand how we are getting that.
See here, what is the PMOS basic width? See, WP by WN equal to 2. So see here,
Okay, that's
PMOS, its basic width is 2W for the symmetric inverter.
okay, ma'am.
That's why here there are 3 MOSFETs means I'm getting 6W. 3 because it's 2W. 2W is giving you R. So 4W will give you R by 2. 6W will give you R by 3.
Oh,
See
there are
here.
two PMOS. Okay, that is just
Okay.
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 I understood.
Now WP by WN equal to 2. If WP by WN equal to 3, it changes again.
Okay.
Is it clear?
Yes, ma'am. It is clear.
Here only there is a conflict. Because in one path it is 2, in the other path it is 3. So which should we take? We should take only 3. Okay. But here there is no conflict at all. All the ways it is only 2 MOSFETs in series. It's so simple. Yeah. Okay. If there are no other doubts, I think I can end the meeting.